So this is lesson 4, and lesson 4 introduces us to a new word. They're called identities. Identities are statements that are true at all times for all circumstances um, in all situations. For example, Pythagoras is true for right angles. So there are some restrictions, I guess. Pythagoras actually only works for 90-degree triangles. So we've started with Pythagoras a long time ago. Pythagoras said that a squared plus b squared equals c squared with a specific relationship as to what c was. We've taken that into our unit circle, and we've drawn a unit circle. X squared plus y squared equals r squared. Our unit circle is defined by a radius of 1. So we've said x squared plus y squared equals 1. But our unit circle work has shown us that x over 1 squared plus y over 1 squared is actually equal to our first identity. What's x over 1? X over 1 is actually the definition of cosine. And y over 1 is the definition of sine. So we have in Pythagoras our first Pythagorean trigonometric identity, which is cosine squared theta plus sine squared theta equals 1. Now we can manipulate with other known quantities. They're called quotient identities, like tan theta equals sine theta divided by cosine theta. That's a quotient. Another quotient identity would be cotan theta is the reciprocal of that, cosine theta over sine theta. And then even the definition of cosecant and secant are reciprocal trigonometric identities as well. What I've done is I've tan theta, the tan theta statement for sine theta. So I've isolated for sine theta, and I've plugged that into my first Pythagorean trigonometric identity from on top here. So now I have cosine squared theta plus tan theta cosine theta, a replacement for sine squared, still being equal to 1. The squared comes in on both of my trig ratios, which is cool. Cosine theta squared plus tan theta squared cosine theta squared equals 1. And now I have some cool factoring to do. Pull out a cosine squared. Well, that looks interesting. What's left? Well, what's left is 1 plus tan squared theta. And with a little bit more manipulation, namely moving that cosine squared theta over, I get my second trigonometric identity. Was up here. My second one is down here. Do I have to memorize these things? I hope not. They're actually on your formula sheet. Let's look what else I can do with the starting of the trig ratio. So I still have the sine squared statement, and I'm going to take my tan theta statement, and instead of solving for sine, I'm going to solve for cosine. Solving for cosine isn't nearly as nice. Cosine theta is equal to sine theta divided by tan theta. But it gives me a substitution for cos theta, which apparently is cool. Apply the squared to the numerator and the denominator, which looks good. And I see that in the bottom there, I've got sine squared as a common factor. I'm going to pull that out. So factoring out a sine squared leaves me with 1 plus 1 over tan squared theta. Well, I know what 1 over tan squared theta is. That's the reciprocal of cotan, so I'm going to write it as cotan. And then I'm going to move the sine over to where the 1 is, and I've generated my third trigonometric identity. This is my third trigonometric identity. 1 plus cotan squared theta is equal to cosecant squared theta. Well, what are we going to do with these identities? We're going to prove statements are true. Prove identities. Let's see what that looks like. So here we've got a much nicer statement of what an identity is. An identity is true for all values of the variable x. It might have restrictions, like Pythagoras has restrictions. You have to be working with a 90-degree triangle. That's a restriction. We have some basic identities, and we've actually built some identities. If we slide down a little bit here, you'll see what we already know: sine, cos, tan, Pythagoras, and the reciprocal trig identities, which we already are aware of. But we want to look at the method of dealing with identities, and that's proving that the left side is equal to. All right, so we're actually asked to verify that this statement is true. We actually can't assume that it's true, and what we want to do is evaluate independently the left and the right-hand side, and you must leave the material that's on the left-hand side on the left, and you must leave what's on the right-hand side on the right-hand side. So I'm going to switch to degree mode and try this out. Tan of 60 special angle. That I'm going to show it. Sorry, I've got my cord tangled here. Let's see if that's better. So the tan of 60 is root 3 or 1.73. So root 3 or 1.73 and some change. Need the sine of 60 and the cosine of 60. So the sine of 60, you might remember, is root 3 over 2 from your and the cosine of 60 is a half. By special triangles, and now working with my knowledge of fractions. Multiply by the reciprocal, multiply by the reciprocal. I actually get root 3 on this side as well. So I get to end this statement by saying my left side equals my right-hand side, and that's proved. We'll try out that first trigonometric identity. Take the tan of pi over 6. So let's see if you can remember what the pi over 6 values are. So from my unit circle, the tan of pi over 6 is 1 over, 1 over squared, and to that I have to add 1. 1 over 3 plus 1 is equal to 4/3. Breaking up a little bit here today. The secant of pi over 6. The secant of pi over 6 is 2 over root 3. Find that on your... Maybe I have a dead spot there. 1 second. So the secant of pi over 6 is 2 over... and did go dead again. And then I have to square 4/3. And I've generated the same thing on the left-hand side and the right. So from time to time, problems with denominators. So the identity for tan theta is fine as long as cosine theta does not equal 0. So there's a problem when cosine theta equals 0 because it be undefined. So from time to time, restrictions in mind for identities, but it's things like denominators and right-angled triangles. We actually proved the 1 plus tan squared identity already using Pythagoras, and you'll have opportunities to do more later. Let's see if we can find a problem to do. So I should talk us through a couple. Proving identities is a little bit of an art form. I like the art. Sometimes you start on a track and it works. Sometimes you start on a track and it doesn't work. Some suggestions. Write everything you can in terms of sine and cos. So sine squared over cos squared is already sine and cos. I'm going to write 1 as a fraction. I chose to make it cosine squared over cosine squared, which is equal to 1, because my denominator is now the same. So now I have sine squared over cos squared plus cos squared over cos squared. So my denominator is now the same. And I've been able to use that Pythagorean identity that sine squared plus cosine squared is actually equal to 1. So my numerator changes to a 1. My denominator is still cosine squared. And I'm left with secant squared x as my answer. I wasn't sure my path would work on B. Suggestion, write everything in terms of sine and cosine. So cotan turned into cos over sine. That's a quotient identity that you have on your formula sheet. I made a common denominator for my fraction, so I multiplied sine x by sine x so that I could have a common denominator. So that's sine squared x plus cos squared x over sine x. Again, my numerator is 1. That's a fantastic result. And I get to replace my numerator with 1. My denominator is sine x. And I'm left with cosecant x in the denominator. So the next example suggests something similar, right, in terms of sine and cosine, and then get it to simplest form. So I'm starting my work. I replace the tan x on the top, or tan a, sorry, with sine x and cosine x. Sorry about the variable switch there. And then I've got a tan squared a, or x. So I've written that as sine squared x over cosine squared x. Now what should I make the 1? Should I make the 1 sine over sine or cos over cos? It seems to make sense to me to make it cos over cos squared. So writing that as cos squared x over cos squared x makes sense based on our previous work, because I can now write 2 sine x over cos x in the numerator, divide by a single denominator in the denominator, cos squared x. But I've got cos squared x plus sine squared x. Well, that's cool. That's 1. Cos squared x plus sine squared x is 1. And now I can perform some reciprocal work. Multiply by cos squared x over 1. Multiply by cos squared x over 1. And I have some things that cancel. The 2 is still there. The sine is still there. And I'll have a single cos. One more quick example here, and then we'll try out some questions, I guess. Factoring. We're used to factoring. What can I factor first? I can take a 3 out, so I did that. Then I recognized that as a difference of squares, which was good. Square root of the first one, square root of the second one, join them first with a plus and then with a minus. Then I recognized that this is an identity I'm trying to learn. Cosine squared theta plus sine squared theta is equal to 1. So that gets replaced. And then I have another difference of squares. Cosine squared theta minus sine squared theta, square root of the first, square root of the second. Join them first with a plus and then with a minus. And then we're done. The answer simplifies into what you see. I'm going to try the last one. I just have to move my recorder. That's how that one looked. Sine squared. Just having some trouble with interference or pickup. Sine squared. And 1 plus cotan squared. And 1 plus cotan squared is an identity. You need to have your formula sheet out so that this works for you. Is what I was left with. And cosecant squared is 1 over sine squared. And when I look at their relationships, for sine squared gives me a 1. That one simplifies very nicely.